After that, I will I do a board when I'm sitting here, by the way.
Yeah.
Did you also download WhatsApp, by the way?
Yeah, I did download the WhatsApp.
You did? Okay.
So is there anything else that I need to do?
No, I think I can add you now.
I should get.
No, you're still not popping up.
I think they fixed the TV.
Your name is Ryan.
Yeah, right.
Maybe.
You have to-
Keep it here. Let's, oh yeah, now you don't have to see it, right? Let's see. What do I do?
Wait, maybe, oh wait, I can make the other one. Yeah, I can do that.
Light sense. Still like it.
Ryan?
Yeah.
Cool. Now I have.
So you can control using them, right?
Oh.
They uploaded a homework, so they will make it due on Tuesday. It's an index notation. It's relatively easy. I think problem one is very lengthy, but should be straightforward. But problem two probably might be challenging. But check it out.
Did you post it already?
Yes, I just now posted, I think maybe 10 minutes back. One. This is when I write this small, is it readable for and Abdullah?
Yeah, it's fine.
Yeah, my glasses on. Yeah, I can see it.
You still are doing review? Still not
Yeah.
start working on the proper Maxwell's equations yet. Last time we talked about index notation. Here we will talk about dyadic notation, and we pretty much work with both notations simultaneously. And maybe more of dyadic notation, that's possible, but it's not very clear to me actually which one is used more. So let's say equally. So dyadic notation is it's pretty much a symbol for a tensor. It has two index, and the best way to write it is let's say Yeah, we already have a tensor. This will be equivalent to, this means equivalent, right? It's not exactly equal because the two notations being mixed up. That's I. Okay. So this I stands for this vector here, J stands for this vector there. It stands up. Usually you don't say I and J there, but that's what it means. That's a qualitative picture that I want to say, but Dyadic notation has this slightly superior, let's say, construction. It is a superior construction in the sense that it is not basis dependent. Okay, so think of, let us say, a construction like, let's say, in your homework, for example, let's say you have a dyadic, which is E and B. Mathematically speaking, it means it's a cross product, outer product of E and B. So this is equal to E outer product of B. That means all possible combinations of the components of E and B. That's what it means. But we will not write this, we will just write it here. Notice that there is no scalar product between them. There is no vector product between them. These are literally two vectors hanging around each other. And the position of the matters, if B is on the right, E is on the left, it's not the same as when you interchange them. So this is not equal to, like this is not equal to B times E. So the position of B and E matters. If you have electric field to be EX in the X hat direction plus EY in the Y hat direction, Y hat plus EZ in the Z hat direction, then you can come up with some immediate constructions. For example, Z hat dotted with T is equal to, notice the dot is on the left. So I can say this means that Z hat dotted with E times the magnetic field, which means that Z hat is EZ. Notice this is a vector, right? I have contracted or taken a scalar product with the left and with the index on the left if you want. I still have a vector remaining on the right, so I have a vector remaining. I can do another quantity here, so that's T. That's equal to EZ times EZ. Or and by that I meant that there is a magnetic field construction here. But notice that one might say that, oh, this is a scalar, but this is not really a scalar in the sense that this is a component of a vector. So this should be read out as this is a component or projection of T along the hat on the left and the hat. For example, a vector A dot, or let's say E, right? E here. E dotted with X, is that a scalar or a vector? Or is it a component of a vector? It's a component of a vector. You don't say scalar. Scalar by definition is something that is invariant under rotation. So ex squared plus ey squared plus ez squared. That's the scalar. But a component of a vector, if you rotate it, if you rotate your axis, that will change, right? That will be smaller or bigger. So it's a component of a vector. Similarly, this is a projection or a component in the x, z hat and z hat direction. And typically we in the beginning often work in rectangular coordinates, and usually vectors are these constructions are good, but Dyadic also has this feature that you can actually talk about r hat dotted with t. That's the component of or the projection of the dyadic t in the direction r hat. You can take a vector and take a component in any direction. You don't have to be talking about x hat alone, right? So for example, E in the direction of r is a component again. It could be a scalar if it was radially, if there was only a radial component to that. But in general, that's only a component of a vector in the radial direction. Similarly, this is a component of t in the r hat and r hat direction. Any questions at this stage? Right? It's a very simplistic idea, but now I want to talk about a couple of operations which will be useful to work while we are working in dyadic notations. Okay, so let me go to the next code. So let's often we work with electric field. So let's say we have electric field, and it's usually not necessarily a construction that is best suited in rectangular coordinates. For example, you have due to a point electric field due to a point charge is 4 pi epsilon naught times let's say q over this times vector r over r cube. All right, that's the electric field. And then a quantity that usually we work with is gradient dotted with the divergence of the electric field. That's something we want to work with. And if we evaluate this, that's a constant. That's 4 pi epsilon naught. And we have divergence of r over r cube. Okay. This involves two constructions. So think of a derivative of a function in the numerator and a function in the denominator, or you can say a multiplication of two quantities r and 1 over r cube, right? That's how you can see this. So distribute it.
That was on our quiz too.
Yes, so I want to, so was that done very comfortably? If it was already, there is a chance that you maybe did in a very long way. I haven't got a chance to look into your quiz yet. I should have. It would have been very beneficial. But what I'm going to stress here is that I will use a couple of identities and then be able to do these manipulations in a few steps. That's going to be the point I'm trying to convey. So yeah, so this is 4 pi epsilon naught. So this is, if I take, so notice I'm saying r times r cube is equal to a product of two quantities. It is r and 1 over r cube. Derivative distributes. So it is dot product.
It's also equal to R hat over R squared.
Yes, and I would say, correct, it is. This is also equal to R hat over 1 over R squared. That's, but I will in a minute convey why I would like to write it as R over R cubed. Okay. So this involves, I can evaluate this 1 over R cubed, or I can do the, I can hit it on 1 over R cubed. Right? And leave this alone. And dot with R. Okay, so, clear. So there are two operations I'm interested in. Instead of talking about the divergence of R, let me have the following construction. And now notice that this is a dyadic. Right, there are two vectors. I have not put the dot product here. Could have been a cross or a dot, or I leave it vacant. When I put a dot, that's a scalar. If I put a cross, that's a vector. And now I'm not putting anything there. That's a dyadic. Okay, two vectors, right? Two vectors, dyadic, right? So now it's a dyadic, and I want to evaluate that. So there are 9 components to that, and let's do this in or let me state what this is. This is going to be equal to 1. So that seems like magic, but I'm going to evaluate this in a minute. And my point is that this is what you want to keep this as an identity from this point. Once you derive this, you can always use this. Okay. So why is this so? We want to evaluate all the components, right? Whenever I have a dyadic, I want to evaluate every possible component to that. So the 9 components in rectangular coordinates would be equal to, think of this again. I can have x hat dotted with the gradient times or vector r. First, I would evaluate this and then take the dot. Or I can have x hat dotted with y hat, or I can have that's 3 of the possibilities. I can also have y hat and so on. And 3 more. But what is this equal to? That is, these are the components. So in a sense, this is the matrix, right? And that's what a dyadic has, this 9 components, but this is in the basis of x, y, z. But what is this equal to? Let me find some space. Let's go this way. So it's equal to the first component is nothing but d by dx of the vector r. And then you take the dot product with respect to x. But let me just evaluate that instead of doing this completely. What is that equal to? That's equal to d by dx of x hat plus y hat plus z hat, right? That's your r. Take the derivative and then take the dot product with respect to x hat. Huh?
The second part, there should be a Q over 4/5.
Oh. Good catch. Thank you. Thank you. Yeah, otherwise it's dimensionally wrong. That, yeah. Good, okay. But let's come back to this. So this is now, and yeah, this doesn't affect anything else, correct?
No.
Okay, good, yeah, okay. This is equal to derivative of this vectors. This whole thing is inside in here, right? Derivative of x. What is derivative of y with respect to x? 0. The assumption is that these are free variables. One is independent of the other, and that's equal. Then this is 0. That's 0. That's equal to x hat dotted with the x hat, and that's equal to 1. And you can see this immediately that each one of them will evaluate in that manner, and this is equal. Oh, sorry, this is r. That's equal to, as far as the dyadic or the matrix construction goes, 0, 0, 1. Quiz. Do the rest of the components in a sense, like I did the first component. That's almost straightforward, trivial. And this is what is written as 1. Now, interesting part here is that, and by the way, this is more explicitly. Oh, did I? How did I? Yes, this is okay. Notice that I have done the x dotted with x in here. If I do not do this components explicitly, if I leave this open, that is to say this dot x is not there, you will notice that this will come out with x hat times x hat plus y hat times y hat plus z hat times z hat. This is not obvious right away. This is a statement of completeness. And we will use this all through whenever. So we are saying that the gradient operator on the position operator is equal to this quantity in rectangular coordinates. For that matter, if you're in spherical polar coordinates, it's equal to r hat plus theta hat plus phi hat. If you're in cylindrical coordinates, this is rho hat plus phi hat plus z hat. With the understanding that this is in spherical polar coordinates, it's r theta phi, and this is rho phi z. This is cylindrical coordinates. We will mostly work with only these 3 coordinates: rectangular coordinates, spherical coordinates, and cylindrical coordinates. And the understanding would be that this is always true. And this is, if you compare this with quantum mechanics, this is the completeness statement exactly as we write in quantum mechanics. This is now in a finite dimensional vector space. There are only 3 unit vectors. The idea is pretty much the same, but we are writing in this form. And if you're in quantum mechanics, you would say this is written in this form, right? So this is I and I, and you will sum this up. And you will say that this is equal to 1. How do you write 1 more? That's just 1, right? That's just 1. Yeah, you can. I mean, Schwinger would write it like this. For like 2 bars, but it's just 1. It's not 11. What is that? Just 1.
What are the brackets?
Oh, what are the brackets? Good one.
We're not there.
Okay,
Projects.
you get. What are the brackets then?
Well, not brackets, I meant, what is the
Yeah.
the sign next to the I, but.
Yeah, so how do you, okay, practicals. We could consider if this is 2 vectors, right? You're keeping adjacent to each other, right? One is on the left and one is on the right. And if you want to be very visual about it, you want to say that one is acting on the left and one is acting on the right. So you say that, let's write this as, instead of our hat. So let's make this very clear. We're saying that one is on that side, one is on this side, right? So it's kind of building a space around it. So just a notation, it's called the bracket notation in quantum mechanics. So now you're saying r theta phi, then you say that, oh, I don't want to write r theta phi, I'm going to write 1, 2, 3. So if that's a notation, then you would say that this is a summation over this I, where I runs from r hat, theta hat, and phi hat. Right? So that's a broad notation, and then in this way you would say it's just 1, and let's stick to the vector. It's the same. Yep. This is not we won't be using this at all, but in this room there are many who have done quantum mechanics before taking this course. Then they have some insight when you write it in this form, and this is the same idea. That's the point. So everything there, if you have built some insights, that will be useful and here, but in a finite dimensional space, quantum mechanics typically, not necessarily spin, it is finite dimensional, but typically most often it's infinite dimensional space.
And used to represent a complex vector.
Correct, and then you have this, yeah, you're right. These are Hermitian conjugates, and yeah, all that understood. There is a complex conjugate features to this. Yeah, these are real, so significantly simpler. It will be orthogonal set of vectors instead of Hermitian and unitary set of vectors. So unitarity will be orthogonality here. Hermitianity will be the symmetric part of the tensor. So the tensors will be symmetric. Okay, good. So with that, so in that sense, this is useful. And notice again that this lets us go from one coordinates to the other. It is not restricted to the rectangular coordinate. On the other hand, the index notation is very much dependent on it being in rectangular coordinate. So that's a drawback of index notation, unless you get creative and make sure that you're working in that space. Okay, so this is a dyadic. This one, notice again, no operation here, but if I do an operation there, I take a scalar product. What is that equal to? Right, I have to actually put in a dot in between, right? So in between all these vectors, so this is x hat dotted with x hat plus y hat dotted with y hat plus z hat dotted with z hat, right? That's what that dot product means. This is 1, that's 1, that's 1, that's equal to 3. Okay. This is also the trace of this unit dyadic. So this often we will say this is also equal to the trace of the gradient and the vector r. For that matter, it could have been any vector a and b. The trace of the dyadic construction using of a and b will be a dotted with b, or the sum of the diagonal elements a1, a1, b1, b1, or a1, a1, a2, a2, and a3, a3. That's what it would mean. So overall, we have this will play a central role in the whole course. Okay. So whenever you get this, you want to think of this as 1, right? That will play a very central piece. I cannot stress that the importance of that. I'll keep repeating it. The whole first 2 weeks, this plays a very central role. Okay, so having that, now let's talk about gradient. Now it's a gradient operator of 1 over r. This is a scalar 1 over r, and the gradient of 1, sorry, I didn't mean that. I want to say gradient of a scalar, that's r. It's just the quantity r. This is the magnitude of the vector r. This is the magnitude of the vector r. And this is equal to gradient of x squared. Like, let's work in rectangular coordinates. That's x squared plus y squared plus z squared. If you're working in rectangular coordinates, there is a derivative with respect to x, there is a derivative with respect to y, there is a derivative with respect to z. If I take the derivative with respect to x, it is I hat is x hat, right? So x hat times, when I take the derivative, it is x over x squared plus y squared plus z squared. Is that clear? Like, I take the derivative, it goes in the denominator, and then I have to take the derivative of the argument. It is 2 times x plus y hat times y over x squared plus y squared plus z squared, and z hat is z over x squared plus y squared plus z squared, because it's pretty much the same, except when I take that derivative of the argument, it gives me x y of z, and there is a factor of 2 there, but the power 1 by 2 and we cancel out. But this probably you've seen in the homework. Let me write this more explicitly. This is x hat plus y hat plus z hat over x squared plus y squared plus z squared. The numerator is nothing but the vector r itself, and the denominator is its magnitude. Which is nothing but r hat. Okay. So this is just a something it's useful to remember, but as I said before, this quantity is a completeness statement, has a lot more importance in the constructions we are talking about, but this is just an identity which will be useful. So 2 quantities which will be useful is going to be, this is 1, and the second is, if you take the gradient of the magnitude of r, you get vector r over r itself or r hat. Okay, so this will be very useful, even though I spent few minutes deriving this, but next time onwards, I will be just using, I don't have to derive it. Right, and remember, these are geometric objects, these are not in any basis. It's not necessary that I'm talking in terms of rectangular coordinates or spherical coordinates or cylindrical coordinates. These are basis independent. Right, so that's the advantage of these identities, right? So we don't have to be working in explicit components all the time, if I know this. So now coming back to this identity we were trying, or the divergence we were trying to prove. So we had this divergence of the vector r, that's nothing but 3. So this is equal to q over 4 pi epsilon naught times 3 over r cubed. And as you asked, why did I split it into r and r cube instead of r hat and r square? If I had done r hat, I would need the operation r hat here, but I am more comfortable with r because this is going to play a much more fundamental role. But nothing wrong in if you had done an r hat, you would have to split that again into r and r or evaluate the explicit construction. So since we are going to be using this, I'll prefer to write that as r over r cube. Whenever you see an r hat, convert it into r because we know how to operate on r better than, or it will turn out that it will be more convenient over the unit vector. So whenever you see a unit vector, convert it into r over r. That's all you have to do. And so that's this here. Next term. This is 1 over r cubed, but we know how to operate on the r, right? Not on 1 over r cubed, but then use a chain rule. Right? Just use a chain rule now. So this is q over 4 pi epsilon naught. Use a chain rule. This is minus 3 over r raised to 4. Right? So first pretend as if r is a function, and then the operation on the argument itself, that's r, right? Dotted with the vector r. Is that clear what I did? So I pretended r is a function, that's minus 3 over r raised to 4. But then I have to hit the function itself, that's this. And this I know how to do. Right, that I've evaluated. So this is equal to q over 4 pi epsilon naught 3 over r cubed minus of q over 4 pi epsilon naught. So this is r hat now. So it's 3 over r raised to 4. That's r hat dotted with vector r. That's a vector r, magnitude of r itself that goes away, and this is equal to 0. So let me, we'll come back to this in a minute. I want to discuss this because in your homework, this is 0, right? But apparently it's not 0 when you, like it is supposed to be a delta function, correct? So what are we missing here?
This means r is not 0.
Yeah, so when r is equal to 0, this is really silly, right? When r is equal to 0, there's an infinity here. Apparently there's an infinity there also. So this is probably not valid at r equal to 0, this argument. So at r equal to 0, we have to be more careful. Whatever it is at r equal to 0, we will come back and talk about that in a few minutes. But let me do this example of how these operations are done in another example so that you know how these vector operations go through. Any questions until now? or comments. What I'm emphasizing here is that you want to remember these two. Anytime, anywhere I ask this, you should just know this is a relatively simple identity I'm asking you guys to remember, and you will be able to proceed on every vector operations that way. So that's what I'm emphasizing. Okay, so let me do an example again. So let's say there is a quantity vector R over A divided by A cube. No. Four. How? So it's 1 over R. So 2, so R cube. Dimensions, dimensionally, what is this? What are the dimensions of this quantity?
1 over R.
No, I don't have epsilon. And no, even now you cannot say, right? So let's say A is dipole moment. R is position, A is dipole moment. Then what is the dimension of this quantity?
Potential.
Potential. That's very good because no, not potential, right? Try again.
It's Q over R.
Q over R, right? It's potential, or is it potential energy? So what I meant was that if you have a dipole, right? Let's call that D. And you place it in an electric field, right? Let's say this is uniform. It doesn't have to be uniform at all. But for the time being, let's say it is uniform. What is the force exerted on a dipole in a uniform electric field? Force.
That force would be 0.
Very good, right? So a dipole is basically a negative charge and a positive charge, right? That's all. And separated by a distance A, that's negative Q. That's plus Q, right? An electric dipole is two charges of equal and opposite magnet, or equal and opposite charges, if you want. And the direction of the electric dipole is from the negative charge to the positive charge. And they're separated by a distance A. Now, a positive charge in an electric field experiences a force which is in the direction of the electric field, that's Q times E. Right. And this E is the electric field at this point. The position of the charge decides what's the force it's going to experience. So the electric field at this point. Same thing here, this time it will be exerted on that side. So that's Q times E, but this time the electric field evaluated at this point. But if it's uniform, both the electric field are exactly the same and they cancel out. If it's not uniform, then these two electric fields are not the same, and then there is a gradient of the electric field that comes into picture, and that's a force that it experiences. So the force experienced by a dipole is 0. So does that mean nothing happens?
We have rotation.
Rotation, right? So you're trying to pull it this way, that is a slight displacement here. when you try to pull this way, the forces here balance out. And there is a couple here, right? So it's trying to rotate, right? So it tries to rotate that. So it's not that nothing happens, something does happen. So a dipole moment, even in uniform electric field, interacts. For that matter, it interacts for any electric field. It doesn't have to be uniform at all. So what is that interaction energy between a dipole moment and an electric field? It's called the Stark effect, but we don't have to talk about that. So what's the interaction energy, potential energy between D dotted with E? So the potential energy is D dotted. This is electric field dotted with the dipole moment. That's the potential energy. So the unit is joules, right? Or dimensionally, that is the energy. Still, there is something missing in there. Small, trivially. Small, but very important.
Potential energy of the electric field.
Potential energy. Now, unit vector. Unit vector, that's a scalar, right? Energy is scalar. Correct. So no unit vector. So she's a charge, but dipole moment is A times Q, right? So let's say this is D, let's say. Okay. D. Vector D. Dipole moment. What is wrong in this? Not the units. Something simpler. Maybe I put a gap there. That helps.
Negative.
Yeah, very good. Negative, right? Yeah. So that's a sign, right? So it's a negative energy. Good. Okay, so that's the potential energy. And let's say the electric field is not dot uniform. If it is not uniform, it will experience a force, which will, intuitively speaking, it will depend on how much electric field changes in that tiny distance A. Right? That's what it will depend on. But how do we see that? Force and potential energy are related by gradient, negative gradient. Right? So always, only if it is potential energy, not the work done. If it's a work done, we cannot actually define, always define a force. It's not two-way. But if there is, if it is path independent, that's what it means. If you can define a potential energy, then the force is a negative gradient of the potential energy. So we should be able to calculate the force by taking the gradient, right? So let's take the gradient. So negative cancels out. So it is 1 over 4 pi epsilon naught times the gradient of R dotted with D. And let's say D is a constant, like D is the property of an atom, let's say, right? So it cannot depend on position. It's a property of an object. So that's a very useful quantity, and we should be able to evaluate this, right? We need vector operations to be able to evaluate this. And now, if you do not know the identities that I gave you, it might be a little laborious, a little tedious to do this. But I'm going to illustrate that with the identities that I gave you, just 2 identities, we should be able to do this relatively quickly after some practice in 2 steps in principle. Okay, so That is R here, that is R cube here, that's the only two places that position comes in. D is a constant, right? So evaluate that. So I have 1 over 4 pi epsilon naught. And this operates on R, that's gradient of R, right? Remember, this is a dyadic, right? And dotted with D over R cube. That's the first term. And the second term is I have to hit R cube. Right, so this is plus 1 over 4 pi epsilon naught gradient 1 over R cubed and R dotted with D. Okay, notice I have not used any coordinate system. I'm working coordinate independent, like or basis independent. I'm not in rectangular coordinates, I'm not in spherical coordinates, I'm not in cylindrical coordinates, so big advantage there. And I have not used any big concepts until now. This is standard distribution of differentiation, right? I'm pretending that this is a differential operator, just distributing. And at this point, I evaluate, I use my identity that this is 1, right? And unit dyadic dotted with a vector gives me the vector itself, right? That's the feature. So that's equal to 1 over 4 pi epsilon naught. So let me do this in 2 steps. 1 dotted with D over R cube. And here, this is minus, right? So this is minus 3 over R raised to 4. That's 1 over 4 pi epsilon naught. Minus 3 over R raised to 4. And then comes gradient of R. That's R hat, basically. And then R dotted with D. That's clear. So this is nothing but 1 over 4 pi epsilon naught vector D over R cubed. This is R hat. Use one of the R hat. This is also R over R. Now I convert it into R hat. So it's minus 1 over 4 pi epsilon naught times 3 R hat dotted with D divided by R cubed. Right. That's your force. Notice pretty much, I mean, it seems like it's 5 steps, but with a little practice, you'll be able to do this in 2 steps or 3 steps. Right. So this is the only information I needed. And that's most often when we are doing in elementary physics, we work in rectangular coordinates and it takes some effort to do this, or it's very tedious and you lose the insight in here. Here it's better, so there is part of the force which is in the direction of D, and there is part of the force which is in the direction of R. So there is a radial direction and there is a direction of the D itself. Often this is written as D R minus 3 R hat dotted with D over R cube. And even better, if you want to write this as a projection, this is 1 minus 3 R hat dotted with D divided by R cube. It seems like this is an unnecessary notation here, but it's not, because one, remember, is a completeness statement. I can go to any basis, and it seems like if I am in spherical coordinates, then I have r hat canceling, and this is in each of the directions of the basis. I have a contribution. It is the component of D in that direction that helps you. So that is, there's a geometrical insight in here. So often one minus something is called a projection operator in that direction. Okay. Lot of writing helps elaborate on that more.
I'm saying.
You mean between here to here or something else? Between the whole, yeah, a lot of
The
writing.
whole idea.
Yeah,
Then again, it's physics. So.
yeah. Yeah, that you probably cannot. But it's kind of, the idea is that we are really, this is an inference we are making, right? If we start from the left side, from the first step to the second step, if it is true, that's a logical identity. This means that, or let me stress on that now, right? This is 0, right? So logically, this is 0. So if I add 0 plus 0, I should again get a 0. Do we always get that? 0 plus 0 plus 0, do we get zeros? Is there any way we can get something else when we add a lot of zeros?
Double function.
Yeah, apparently, right? Because that's the answer, right? So let me elaborate on that. I'm going to add a lot of zeros and not get a 0. Okay. Very.
Zero is.
Huh?
At one point it's infinity.
No, I'm just going to add zeros. Oh, at one point it's infinity. Yeah. So you're saying, yeah, correct. Yeah, but I'm trying to say that if I add a lot of small quantities, I think my point here is that if there is a differential element, so in calculus, remember, we make this tiny element in the limit when I'm having very small object, but if I sum it up as many times as I split them into, like maybe the point is I take a carrot and break it into tiny pieces, right? And then we say that, oh, this is dx, and the limit dx tends to 0, it seems like this is equal to 0, but then I'm adding up all these quantities again, I get back my carrot, right? So in that sense, in that limit dx tends to 0, if I add up all those dx again, I can get a finite quantity. So in that trivial sense, it looks trivial at this point, but we're actually adding up a lot, like in integration, we are adding up a lots of zeros in a sense, and then getting back a finite in a very unambiguous way, without any ambiguity. In that limiting sense, it is a well-defined and quantity. So I'll bring this back again. So I want to start from here, right? So let's go back to this. I have 20 minutes. So we showed that if we have a vector field of this nature, Q, and that is R over RQ. We showed that this is equal to 0, except at one point everywhere. This is the whole space we are talking about is equal to 0, except I'm not very sure at R equal to 0. That's one point in space. Agreed? Now that's a quantity. What should I say? gradient of electric field is charge density, right? So rho. Yeah, so let's C of R. Let me not call anything. So that's some scalar field which is 0 everywhere for sure, and at R equal to 0, I don't know. Okay. Let's take a simpler feature of a function C of x, let's say f of x. And let's say I know that function everywhere except at 0. So this is some function here, and this is, I don't know what that function is at that point. Okay. And then I ask, what about integral x times f of x? And let's say I go from minus infinity to plus infinity of f of x. Oh, but then I also know that f of x is 0, right? So this is even better, right? So f of x is 0 everywhere except x equals 0. Okay. So, and then I do an integral of f of x. What do I get? 1. 1. No, I said f of x is 0 everywhere, right? Except at x equal to 0. Huh?
F of 0.
F of 0. Why f of 0? No, it's 0, I said.
No,
Everywhere
it's not
except
direct though.
I have not told anything about the delta function yet. Let's say if it is equal to 0, is that obvious? Is that straightforward? Right? And there is another possibility that it is minus infinity to plus infinity dx of f of x is actually equal to a constant. Let's say 3 for the math. Is that even possible? Like that's the first question we should ask. But let's ask this, is there anything funny about this? Let's have a function. That's what I was trying to allude to earlier. So this is, I don't know about this function only at one point. So let's say this is A. And I integrate this from let's say a minus delta, and this is a plus delta. Okay. Delta is a positive number, so I'm coming from this side, and I'm going to here. So the area, this is an integral, let's say from a minus delta to a plus delta, dx of f of x is equal to, that's this area, and that's slightly away, that's this area. I'm only missing one point there, and I would clearly say that this is a minus delta to a dx f of x, right? This isn't this a theorem that if you have a integral, you can split it into somewhere in between point and then go from there to there. And what if I don't know that point? What if I don't know the value of that integral at that point? Does it matter?
No.
No, because this area, this tiny bit of area is going to be 0. Right? So what I'm missing here is that this tiny area. I go from a minus delta to a to a plus delta, but in the limit delta tends to 0, I can set both to 0. Okay. This is going to be 0. This is a rectangle of 0 width. That's a rectangle of 0 width. And as far as this function is finite at that point A, I have not told you what that function is finite. So this is equal to plus maybe that value of that tiny area here, right? So this area of this tiny element, area of this tiny piece here. This one is going to 0, but this one, it's not very clear what might happen. If it is finite value at that point, that is surely zero, because the width of that area goes to zero. Right? But if it is infinite, it is possible. It's possible, not necessarily. It's possible that that infinity and a zero can go to zero, in the sense that, for example, if you had an area like this, where this was, let's call this D, and the height here was 1 over D. What's the area of this? It is D times 1 over D, which is equal to 1. So only if those areas cancel out very precisely, only then that I can get an unambiguous result. If this was larger than this quantity in the limiting sense, then it's infinity. If this was smaller than this in the limiting sense, that's zero. Right? But if they balance out in a very sensitive, in a very fragile manner, so then these two cancel out and you can get a 1, and that's the limiting, that's how we take limiting values in calculus, right? So in that sense, I'm saying that it is possible that at one point we can get a value only if that is infinity, otherwise it's zero for sure. If the electric field was anything other than infinity, for example, if it was, let's say, billion or very large value, but a constant value, that's not sufficient. It has to be truly infinity, and it has to be infinity in the sense that as you capture that point closer and closer, as that volume goes larger, smaller, that has to be proportional to that, or inversely proportional to that. So this value E at that point A has to be inversely proportional to the volume, or is it the volume, right? That we are to ask. In this case, it was a dx that came in, but in this scenario, we will say it is actually the area that will come out. So with that elaboration, that actually I'm adding all these zeros, and still I can get a finite quantity. So let's talk about, this is now for one dimension, right? But I want to do a volume integral. So I do volume integral of d cubed r. So this is dx, dy, dz, right? I'm doing a volume integral of the divergence of the electric field. I can take any volume I want to. I take the volume to be, so this is a unit positive charge. I take an arbitrary volume, but really centrally about that point. So this is the volume V.
Could you repeat what the integral of d cubed r?
D cube r is
dx dy.
yes, d cube r is dx, dy, dz integrated over the volume V. So split this volume into tiny bit of differential volumes and add up all the values of this divergence on that volume. Okay. But what is that equal to?
Surface integral.
Yes, so there is a theorem that exactly, that's a divergence theorem saying that instead of doing this evaluation at all the volume, I can survive. It is equally fine if I do it on the surface, right? So this is on the surface, but that has a big consequence, because on the surface I know the electric field precisely. There is no issue with R going to zero there. On the surface, I know this precisely. And this is 1 over R squared. The area, the surface area of the sphere goes as R squared. This cancels out. Okay, so this is 4 pi R squared, the radius of that volume, times R dr times R hat, right? That's the volume integral, or the area element if you want to, that's coming from the angular integration. That's your r square, that's a 4 pi r square is the surface area of the sphere. And that's, am I getting this clear, correct?
It's actually volume and surface.
Hmm?
Yeah, should there be like a sign?
What am I messing up? Or d sigma. Yeah. Sorry. So how do I do this?
No, the whole integral.
Yeah.
D is 4 pi r square, right? ESI.
Yes.
So the integral.
If I take out the r component,
Yeah.
right? So let me write this as dA is equal to r square, right, times d omega times r hat. Is that clear? That's the solid angle, like d theta d phi, right? So this is d theta d phi. Did I write this correct?
Yes.
Think so. Okay, r square, dimensionally correct, r square. And d omega, when I integrate, I get the 4 pi, and that's the direction of r hat. I think I got it. So, okay. Good.
Wait,
Comments?
I don't know.
This is the area. Okay, let's see this. More detail.
I don't think that's DA.
The surface is r dr, r sine theta.
Yeah,
Theta.
doesn't say.
The surface of the
Oh,
sphere.
yeah, thank you. Is that correct?
There is dr, right?
It's R d phi, R sine phi.
Yeah, d theta d phi.
dr will not have, dr is in the volume, right? Is that okay? Does that match? Yes. Okay, so that's sine theta. Okay, and electric field is also in the r direction, right? That's the important piece here. So we have r square, d omega, and then r hat dotted with, that is this r vector r over r cube, and that is a q over 4 pi epsilon naught. The interesting part is that there is no angle dependence. All this cancels out. Right, that's a vector magnitude r square, all that cancels out, and that's nothing but q over epsilon naught. Okay. More than the evaluation part, what is important is that I did not use the fact that that goes to 0. It did not use this feature. It only used this feature. Or for that matter, I didn't even use that. So what am I doing here again? I'm doing a volume integral of zeros. Like it's 0 everywhere, except at one point. A volume integral of zeros everywhere on that volume, except at that r equal to 0, I'm saying is not 0. And the only possibility is I have a freedom only at that point r. So it better go as the inverse of this. So that, or 1 over 4 pi of this, so that I can get that result. Is that correct? I think so. Okay. So, so this implies, right, for consistency, right, for consistency between these two, this implies that electric field or divergence of electric field is not actually 0. Right? It is actually q over epsilon naught times a delta function right at that. Is there a 4 pi I have? Q.
That's right.
R this R. Yeah, that's correct. But notice all this is algebra. Again, coming back to Maz's comment that this is a lot of writing. But the point is that if I start from the left, I have to get to the right. I do all the math, if all this is correct. I'm getting a sum of all zeros to be finite, the only way, so that's an inference I'm making. That strong inference I can make only if I start logically from one point and reach to the other, and then I claim that these two have to be the same. And you don't have any other choice. So in that sense, it is very physical, like it has meaning in that.
Why do you assume like the integral of fx is equal to 3?
Oh, that was just a random number I came up.
So if we say like the integral of fx is equal to 0,
Then the
then
missing point has to be finite.
so we divided the integral into few pieces, but the middle part, there's a discontinuity,
Mhm.
so it cannot be 0, something like that.
No, it must be finite, it cannot be infinite.
Oh,
Because even if it is finite, this area, right?
Yeah.
Because this is going to 0.
Yeah.
I don't care how high it is, even if it is millions, billions, how much ever, as far as it is finite, it's not infinity. 0 multiplied by a number is 0.
Yeah.
Right? So it doesn't matter. But if it is infinity, I have a possibility that infinity times 0 could be a finite number in the limiting sense. Right? So when you say infinity times 0 is a finite number, that's meaningless. But here we are saying, so that's the distribution part, like we have to take this in the distribution sense.
so why do you assume like electric field is like 1 over volume?
Oh, that's why I put a question mark here. Is it 1 over volume? Like something that has to cancel. Here it was 1 over x, right?
Yeah.
D times 1 over d. So just taking it blindly to the this, it seems like 1 over volume, but it's not 1 over volume, actually it's 1 over area. Right, so that's why I put a question mark there. So it is not 1 over volume because one of the things goes away immediately using that boundary conditions or divergence theorem. And then electric field goes as 1 over area, which is correct. It goes as the area of the sphere.
What
Yes.
happened to the 4 pi?
Oh, did I miss the, no, because integral of a solid angle is 4 pi.
All right.
Right, integral of solid, like of a unit sphere, surface area of a unit sphere, it's 4 pi, so that gets cancels out. Yeah, right. So you have something which is 0 everywhere except at one point, that's equal to finite. So you have to survive with that, so you define a function which does that job, and that's a delta function. Right, so you don't have a choice to work with mathematically otherwise, so you need that delta function. So you build your mathematics around it. Quiz, right? This might be a little harder quiz. This is divergence. And the curl do the same, which is 0 everywhere except at one point, and you have to build, you need a delta function. Okay.
Pretty sure it's no.
Huh?
Pretty sure it's just no. Thanks.
No, it's yes. The answer is yes.
Oh, it is?
Think of Ampere's law. Hint is Ampere's law. Like this is Gauss's law. Right? So there it is a current that comes in. And you can do the same thing. Curl will be 0 everywhere except at the point, and the same idea goes through. So it's a good thing to have you. This is electrostatics, magnetostatics works with that. But here I was doing dyadic notation, and the emphasis here is that I didn't really have to do these operations, right? I'm able to survive or conclude various things without really doing explicit rectangular coordinates evaluations. I'm able to evaluate this pretty quickly. Only then I can come up with these conclusions, geometric conclusions. So this is geometry. I mean, the way to say it is that this is geometry, not the algebra. Okay, that's all. Thank you. So you guys find small food. I think math has a class. You have a class after this? Who has a class in? No one has a class? You might, oh, sports. Last time I thought we said, okay, so I can extend a little that means 5 minutes at least. I want to do more too. Yeah, but that takes away a little pressure off me. But I'll try not to. So all this is good as of now, like, or making sense. Okay. Next time we will talk about the conservation of charge, right? That statement, and start doing, start using Maxwell's. Now I have the the methodology or the tool to proceed. But next time I write divergence or gradient, I don't have to stop. But so only two identities: the dyadic one and the unit vector. That's the only two identities we will use. The rest everything will follow from it. Okay, thank you. And I have a grade.
Do we get to present that?
Yes, I will. I have not yet graded. I typically am reasonably quick at grading the quizzes. This time I was back. So I'll get it back. I think for you, I will have to personally bring it to the class. Others get it in their mailbox.
Good enough.
Maybe we should get a mailbox for you. That will make it convenient.
It's in the mailbox.
Yeah, so they just have to flip that, right? That might not be bad. Yeah. But then you and I were here, right? So I don't know how convenient it is, even if you have a mailbox. You check it anytime only when we come. We'll see. Yeah, I'll just come and give it to you. That's easy. Yeah. Okay, so does this work out good? Yeah, okay.
Yeah.
So I can switch it up, right?